From this proposition, it will follow, when arithmetical addition has been defined, that 1 plus 1 equals 2. Welcome to this video. In this video, we'll take a detailed look at proposition 54.43 from Whitehead and Russell's Principia Mathematica. I'll be looking at this from the perspective of the first edition of Principia Mathematica. Note that the system of Principia Mathematica presented in the second edition is very different to the one presented in the first edition. I'm more familiar with the system of the first edition, and so that's the system that I'll be considering in this video. This particular proposition often draws a lot of attention and is arguably one of the propositions that's highlighted as a standout proposition in Principia Mathematica. The proposition itself, along with the demonstration as it appears in Principia Mathematica on page 379, is shown on the screen now. The brief comment following the proposition reads, "From this proposition, it will follow, when arithmetical addition has been defined, that 1 plus 1 equals 2. In this video, I'll take a closer look at the demonstration. At this point in Principia Mathematica, Whitehead and Russell are giving more sketch proofs of the propositions, and they're not going into anywhere near the level of detail that they were in the earlier chapters. And this is understandable. Principia Mathematica is already nearly 2,000 pages long, and that's with abbreviated demonstrations, so God only knows how long it would be with unabbreviated propositions. Nevertheless, with this being one of the more significant propositions in Principia Mathematica, I've decided to flesh out some of the details and explain some of the concepts involved. To start to really understand this proposition and its place within the system of Principia Mathematica requires a lot of work beforehand. Some of my other videos cover some of these aspects in much more detail, and I have plans to upload some more videos on Principia Mathematica shortly after uploading this video. So this video is not going to give the full picture. I can't explain every little detail in such a short video as this. If you do feel that after watching this video that you still don't understand the proposition, then if I've badly explained the proposition, then I can only apologise. But if not, then all I can suggest is that you spend some time familiarising yourself with Principia Mathematica. So let's have a look. So the proposition roughly says, if the classes alpha and beta are members of the class defined as the cardinal number 1, then we have that the logical product of alpha and beta equal to the null class is equivalent to the logical sum of alpha and beta being a member of the class defined as the cardinal number 2. So there's a few concepts here that need to be understood. Class, cardinal number 1, cardinal number 2, null class, logical product, and logical sum to start with. The concept of class is in many ways comparable to the concept of set. But the classes of Principia Mathematica are not the sets of modern mathematics. Classes in Principia Mathematica are the extensions of propositional functions. The null class is the class with no members, comparable to but not identical with the concept of the empty set. A class is defined in Principia Mathematica as shown on the screen. I won't explain this definition here because it involves far too many other potentially unfamiliar concepts such as predicative functions and incomplete symbols. If you want to know more about this, then there will be a video appearing on my channel, all being well, shortly after this one, covering the classes of Principia Mathematica in much more detail. The null class is defined as in definition 24.02, and this says that the null class is the negation of the universal class. The universal class, as we see in proposition 24.102, is the class determined by any propositional function which is true for all possible values. An example of such a propositional function is x equals x, and it's this propositional function that is used to define the universal class in Principia Mathematica. The cardinal numbers 1 and 2 are classes of classes defined as follows. The cardinal number 1 is the class of alphas such that there exists an object x such that alpha is equal to the unit class determined by the object x. That is, 1 is the class of all classes with exactly one member. The cardinal number 2 is the class of alphas such that there exist two unequal objects x and y, and alpha is equal to the logical sum of the unit classes determined by the object x and the unit class determined by the object y. That is, 2 is the class of all classes with exactly two members. A unit class is a class with a single unique object as its only member, which in proposition 51.11 we see that the unit class determined by the object x is equal to the class of y's which satisfy the propositional function y equals x. Proposition 51.15 states that if y is a member of the unit class determined by x, then y must be equal to x. Very importantly, classes in Principia Mathematica are grouped together into different types. The type of a class is determined by the type of the objects which are its members, except for the null class, which is determined otherwise. So see page 229 of Principia Mathematica. The logical system of Principia Mathematica is split into various types, which interrelate in a seriously complicated way. There is no single null class, nor a single cardinal number 1 or cardinal number 2. There is a null class corresponding to each type. That means that there's an infinite number of null classes. There's a cardinal number 1 for each type. That means that there's an infinite number of cardinal number 1s, and similarly for the cardinal number 2. The symbols lambda for the null class, 1 and 2 are ambiguous as to type. They have similar meanings for each type and hence the same notation is used, but their specific meanings are entirely dependent upon the type to which they apply in a given context, and therefore the symbols will be understood as automatically adopting the appropriate meaning as context dictates. Whitehead and Russell call this systematic ambiguity and explain the concept in more detail in the introduction to Principia Mathematica, for example on page 44 onwards. I won't be going into any more detail with systematic ambiguity in this video. My other videos do or will cover this in more detail. The logical sum of two classes is comparable to the modern set-theoretic concept of union of two sets, and the logical product is comparable to the set-theoretic concept of intersection of two sets. And to make a clear distinction between the classes of Principia Mathematica and the sets of modern set theory, I will continue to use the phrases logical sum and logical product in reference to classes. So what I'm going to do in this video is to use the demonstration that Whitehead and Russell give in Principia Mathematica for this proposition, but construct my own demonstration which clarifies, to me at least, some of the points which are maybe less clear in the demonstration given in Principia Mathematica. My version of the demonstration is shown in its entirety on the screen now, and I've tried to retain as much of the style of writing demonstrations as I felt that I was able to do, but of course I may differ in some respects. I don't suggest that my demonstration is better than the one given in Principia Mathematica, or that these are the exact steps that Whitehead and Russell intended, and nor do I claim that my demonstration is the only possible demonstration of this proposition. It's just a possible demonstration which roughly follows the steps that Whitehead and Russell take, but with a bit more detail added in. So on the first line of the demonstration in Principia Mathematica, we see that proposition 54.26 is cited. And this proposition states that if the logical sum of the unit class determined by the object x and the unit class determined by the object y is a member of the cardinal number 2, then this is equivalent to the proposition that the object x is not equal to the object y. Proposition 2.02, which effectively says that a true proposition is implied by any proposition, allows us to slip in an antecedent to create an implication. This said antecedent is the proposition which is the logical product of the two propositions that alpha is equal to the unit class determined by the object x and beta is equal to the unit class determined by the object y. And this line I've labelled 1. So next, I've used proposition 22.73, which allows me to assert that the logical product of the propositions alpha is equal to the unit class determined by the object x and beta is equal to the unit class determined by the object y is equivalent to the proposition that the logical sum of alpha and beta is equal to the logical sum of the unit classes determined by the objects x and y. An application of proposition 13.12 with x replaced with the logical sum of alpha and beta, y replaced with the logical sum of the unit classes determined by x and y, and the function phi blank replaced by the function blank is a member of the cardinal number 2. Proposition 13.12 says that if two objects are equal, then this implies that either both objects have a certain property or both objects do not have a certain property. In this case, the certain property is that of being a member of the class defined to be the cardinal number 2. And this assertion I've labelled 2. So now, since both conditionals 1 and 2 have the same antecedent, the logical product of the propositions that alpha is equal to the unit class determined by x and the proposition beta is equal to the unit class determined by y, I can use proposition 4.76, which allows me to assert that this common antecedent implies the proposition that is the logical product of both of the consequents of the conditionals 1 and 2. And now, in this most recent proposition, the consequent consists of two equivalences with a common component, for lack of a better word, which is the proposition the logical sum of the unit classes determined by x and y is a member of the cardinal number 2. So, with an application of proposition 4.22, I can eliminate this common component, giving the assertion that I've labelled 3. Note that even though I'm trying to be thorough with my demonstration, I'm still taking advantage of some of the notational shortcuts that Whitehead and Russell introduce, particularly those introduced in chapter 2, say on page 110. Otherwise, the demonstration would look very cluttered and wouldn't really retain the style of Principia Mathematica. So this proposition 3 is the assertion the logical product of alpha is equal to the unit class determined by x and beta is equal to the unit class determined by y, implies that the logical sum of alpha and beta, being a member of the cardinal number 2, is equivalent to x and y being unequal. And this makes sense, since if x and y are unequal, then they determine different unit classes, and so we would expect their logical sum, which is also equal to the logical sum of alpha and beta, to have exactly two members, and so would be a member of the cardinal number 2. The cardinal number 2, recall, is the class of all classes which have exactly two members. Now we see proposition 51.231 cited, which states that the proposition that the logical product of the unit class determined by the object x and the unit class determined by the object y is equal to the null class is equivalent to the proposition that the objects x and y are unequal. And again, using 2.02, just as before, we can slip in an antecedent, exactly the same antecedent that we did previously, and this assertion I've labelled 4. Now that we have the assertions which I've labelled 3 and 4 respectively, both of these propositions, which are conditionals, having a common antecedent, which is the logical product of the propositions that alpha is equal to the unit class determined by the object x, and beta is equal to the unit class determined by the object y, we can combine these using proposition 4.76 as I did previously. And again, an application of 4.22 allows me to assert the proposition labelled 5. And this proposition labelled 5 says that the proposition that the logical product of the unit classes determined by x and y is equal to the null class, the class with no members, is equivalent to the proposition that their logical sum, and hence the logical sum of alpha and beta, has exactly two members, and so is a member of the class defined as the cardinal number 2. And again, this makes sense, since if the logical product of the unit classes determined by x and y is null, then the unit classes have no common objects. The only object in the unit class determined by x is x, and the only object which is a member of the unit class determined by y is y. And so x and y must be unequal objects, and therefore the logical sum of their unit classes must have as members both x and y and no other objects. Therefore the logical sum of the unit classes, and of alpha and beta, must have exactly two members, and so is itself a member of the cardinal number 2. Although I'm trying to be quite explicit in which propositions I'm using throughout this demonstration, there are still some things that I'm not bothering to mention, such as whenever I use, say, proposition 1.11. If I were to mention every little thing that I'm doing, then this would really amount to nothing less than just quoting every page of Principia Mathematica up to proposition 54.43. If you do want to understand all of those little things that I'm potentially leaving out, then your best bet really is to read Principia Mathematica for yourself. Okay, so now we change tracks for a short while. Proposition 20.43 says that if the classes alpha and the unit class determined by the object x are equal, then this is equivalent to the proposition that z is a member of the class alpha is formally equivalent to the proposition that z is a member of the unit class determined by the object x. We can also formulate 20.43 in a similar way in terms of the two classes beta and the unit class determined by the object y. So these two instances of 20.43 can be asserted individually, and therefore so can their logical product be asserted. Now we use proposition 4.38 to give the proposition as shown on the screen. Proposition 10.4 says that the logical product of two formal equivalences implies the formal equivalence of the logical products of the propositions on the left-hand side of each individual equivalence and the logical product of the propositions on the right-hand side of the individual equivalences. An application of this gives the proposition as shown. And I'll be using the notational shortcuts outlined on page 110 of Principia Mathematica for the next few implications. Next is an application of 22.33, which simply states that the proposition that x is a member of the logical product of the classes alpha and beta is equivalent to the logical product of the propositions that x is a member of alpha and x is a member of the class beta. And so we can see that if z is a member of alpha and z is a member of beta, then this is equivalent to z is a member of the logical product of alpha and beta. And if z is a member of each of the unit classes determined by the objects x and y, then this is equivalent to the proposition that z is a member of the logical product of the unit classes determined by these two objects. And then another application of 20.43 gives the consequent that the logical product of alpha and beta is equivalent to the logical product of the unit classes determined by the objects x and y. So now an application of proposition 13.12 again, with x replaced with the logical product of alpha and beta, y replaced with the logical product of the two unit classes determined by the objects x and y, and psi blank replaced with the function blank equals the null class, or blank equals lambda. This gives the assertion which I've labelled as 6. And again, proposition 13.12 tells us that if two objects are equal, then this implies that they have the same properties. In this case, the property is being equal to the null class. So assertion 6 seems to make sense, since the classes alpha and the unit class determined by x are equal, and also we have that beta is equal to the unit class determined by y. Then if the logical product of alpha and beta is the null class, that is, the class with no members, then the logical product of the two unit classes must also be the null class. So now I can do a similar thing to what I did earlier with propositions 1 and 2 by using proposition 4.76 with the propositions which I've labelled 5 and 6, and then use proposition 4.22 again to give the assertion as shown. This assertion says that the propositions that the logical product of alpha and beta is the null class, then their logical sum must be a class with exactly two members, and so must be a member of the cardinal number 2. And this makes sense, since if the logical product of alpha and beta is null, then these two classes have no common member. But alpha and beta are equal to unit classes, as per the antecedent, and so alpha and beta must contain exactly one member each, and if their logical product is null, then their respective members must be unequal. Therefore, the logical sum of the two classes alpha and beta must have exactly two members. Now, this most recent assertion is asserted of any x and y. Then proposition 11.11 says that I can assert for all x and y. In Principia Mathematica, 11.11 states, if phi zw is true, whatever possible argument z and w may be, then phi xy always is true. This proposition can't be reduced to a purely symbolic form. This proposition is, I believe, only really relevant to the system of Principia Mathematica in the first edition. If anyone knows more than I do about the second edition, which is very likely, then please let me know whether this proposition is still relevant in that system also. I'd be very interested to know. So now proposition 11.35, which is better just presented in its symbolic form on the screen rather than me trying to clumsily say it, can be applied to give the assertion as shown. And then proposition 11.54, again, better just shown on the screen rather than me saying it, can be applied. And finally, an application of proposition 52.1, which states that if the class alpha is a member of the cardinal number 1, then this is equivalent to the proposition that there is an x such that alpha is equal to the unit class determined by the object x. So for example, since we see in the antecedent that there is an x such that alpha is equal to the unit class determined by x, then alpha is a member of the cardinal number 1, And similarly for the proposition, there is a y such that beta is equal to the unit class determined by y, which also appears in the antecedents. A simple application of definition 20.04 to the antecedent of the line labelled 7 gives the proposition 54.43 that we are after. So, from this proposition, it will follow, when arithmetical addition has been defined, that 1 plus 1 is equal to 2. And that brings us to the end of this video. If there's anything that you'd like to ask about anything in this video, then please leave a comment in the comments section or drop me an email. Please remember to subscribe and hit the like button to show your support for this channel. I do try to upload videos as often as I can, but of course they do take a lot of time to put together. But if you do have any ideas about things for me to cover in my videos, then please let me know. Thank you for watching.